Welcome to today's physical science lesson. My name is Mashudu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Today we'll be revising chemistry. So that is our purpose for the day. You will be writing a paper out of 150 marks, of which you are saying you'll still have your 20 marks for multiple choice, 130 marks for structured questions, the total of 150 marks. You will still be writing for 3 hours. Remember, we said you have 1.2 minutes for every mark. So don't forget that. You must time yourself so that you are able to write and finish the entire paper. Now, in terms of paper 2, your scope for our June exam is that we have metal materials, which is your organic molecules, which is half of the paper. So it's very much important. You must know almost everything in terms of organic molecules. You cannot leave anything because there will be many questions that will come from this topic. You are having chemical change as well, which is half of that particular paper. Remember, when you say chemical change here, we are referring to rates of reactions. We are referring to chemical equilibrium. We are referring to acids and bases. And this will include your stoichiometry as well as your energy change, which is what you have done in grade 11. You remember the potential energy diagrams and all that. So that will be part of this paper. And we are hoping that you will revise and make sure that you do well in paper 2. And this session will be discussing skills as to how do you go about answering questions, and then hoping that you will use those skills as you prepare for your second paper. Now, last year's paper, let's look at June 2024's chemistry exam, where the paper, as I indicated, question 1 was multiple choice questions based on all the topics that I referred to: your organic molecules, your rates of reactions, your chemical equilibrium, your acids and bases, as well as your stoichiometric calculations. Now, if we check there, you will see that we have nomenclature, which is question 2, naming of organic molecules. There, in that, we had the empirical formula as well. So it's important that we deal with the issue of empirical formula so that you know how to determine the empirical formula. Nomenclature was 22 marks. We had physical properties. Remember, in organic chemistry, we're doing 3 physical properties. That is your melting point, your boiling point, and your vapor pressure. So we'll talk about that as well, more especially on the skills of how to answer questions. Because the main thing is, if you can know how to answer questions, if you can have a skill of answering the questions, you'll be able to answer all the questions that you'll be asked. We'll be looking at the reactions of organic molecules, and then we'll last year as well there was integration, there was percentage purity there. So it's important that even today we look at percentage purity. We'll look at rates of reactions, which we had dilution there. You will remember C1V1 equals to C2V2, the dilution formula. Then you had to use it there. So it's important that you have that skill as well. In question 6, we had chemical equilibrium. And then here there was a Kc calculation with initial number of moles of product, meaning that it was not zero, the initial number of moles of the product. So it's important that you start to lean around that way so that you don't always think that at all times the product will be zero, because we can have equilibrium, and when equilibrium is disturbed, we'll have a new equilibrium. So the first equilibrium then being the initial. So it's important that it's not all the time that we will always have a zero for the products when we are doing your rice table. So we'll refer to that as well. And then there was as well drawing of potential energy diagram. Potential energy diagrams for your endothermic, your exothermic, when the catalyst is added. So it's important that you go and you revise the potential energy diagrams with or without a catalyst. And we are saying acids and bases. We are doing the entire acids and bases here. We're including even pH. We're doing neutralization. We're doing hydrolysis. We're doing conjugate acid base pairs. So there's nothing we're leaving out in terms of acids and bases. So you have to revise the entire topic. And then we won't be having redox reactions in terms of this paper. We'll be focusing on energy and change. So there will be that topic of redox reactions. Now, With no wasting of time, we'll start with our first topic, which is organic molecules. As I indicated, we have naming of organic molecules and isomers, which is under which was question 2. And then physical properties, as I indicated already, that under physical properties, we're looking at 3 of them, which is now your melting point, your vapor pressure, and your boiling point. And then organic reactions, we'll be looking at our reactions. You'll remember in terms of reactions here, we are focusing on addition reactions, we are focusing on elimination reactions, we are focusing on substitution reactions, as well as combustion or oxidation reactions. That is when your organic molecules, in this case alkanes, will be reacting with excess oxygen to form carbon dioxide and water. We will as well look at esterification, which is when a carboxylic acid reacts with a primal alcohol for our syllabus, and then we're able to form an ester and water with the presence of a catalyst, sulfuric acid. So it's important that you know all this and you are able to answer any other question that will be asked under organic molecules. As I indicated, that there will be a lot of marks that comes from here. So it's important that you spend time with organic molecules and you revise and you are ready and you go and collect as many marks as you can. Now, in terms of definitions, we are always saying our definitions, you must define according to the exam guideline. So we're saying always follow exam guideline when you're writing your definitions. So we're still emphasizing you can't go to write exam without knowing what a homologous series is. Here, we're saying these are series of organic molecules that can be described by the same general formula. They can be described by the same general formula. Those are homologous series. Remember, we are doing 9 homologous series, which is your alkanes, your alkenes, and your alkynes, your haloalkanes, your aldehydes, your ketones, your esters, your alcohol, and your carboxylic acids. So you have to know that these within a homologous series, all of them will have the same, will be described by the same general formula, and then each member will differ from the other by CH2 group. So it's very much important to understand that if I'm talking about alkanes, they have the same general formula, which is your CnH2n plus 2. If I'm talking about alkenes, we'll say CnH2n. Alkynes, we'll say CnH2n minus 2. So you got to know all those 9 general formula for all those 9 homologous series. And then we are saying these homologous series, how do you differentiate between them? We are saying you differentiate between them using a functional group. Now, a functional group, we said, is a bond, is an atom, is a group of atoms. Don't forget, it's a bond, it's an atom, it's a group of atoms that determines the physical and chemical properties of an organic molecules. So the physical properties, which is in your question 3, are determined by these bonds, by these atoms, by this group of atoms that we refer to as functional groups. So functional groups are very much important because how the melting point, the boiling point, and the vapor pressure, our physical properties, depends on this functional group. You will have seen when you are doing your studies to see that if, for example, you are having OH as your hydroxyl group, as your alcohol, if you are having your alcohol there, you know that you will have a hydrogen bond, hence you will have a higher strength of intermolecular force. So it's very much important to understand the importance of this functional group. Even during reactions, the reactions and how these homologous series or how these organic molecules react depends as well on the functional group. Hence, we are saying functional group are a bond, an atom, a group of atoms that determines the physical and chemical properties of an organic molecule. Now, you know the definition of hydrocarbons from its name already. You see, these are organic molecules that are made up of hydrogens and carbons only. We always emphasize the importance of only there to say you can't define a hydrocarbon without emphasizing that it is made up of hydrogens and carbons only. So these hydrocarbons, we're saying they can be saturated or unsaturated. Remember, we saturated, we are saying they have no multiple bonds between carbon atoms. our saturated organic molecules have no multiple bonds between carbon atoms, whereas our unsaturated hydrocarbons, they have multiple bonds between carbon atoms. So it's very much important that you have that understanding and you are able to define all of this. And then we are saying we have structural isomers. Structural isomers, in terms of the isomers, you will have seen iso means same. What is same? Same molecular formula. So what are we saying? We're saying structural isomers have the same molecular formula but different structural formula. So we have three types of these structural formulas, which are structural isomers, which is now your chain isomer, your functional isomer, and your positional isomer. And we are saying as you define all of these isomers, you will always start by saying same molecular formula. That's where you will start. You will always say same molecular formula, but then you look at the name itself, say what is different in that structure. For example, chain isomers, you will say these are organic molecules with the same molecular formula, but different types of chain or different chain length. And then examples there is when you're having your straight chain and your branches. Definitely, they will have different types of chains. Positional isomer, not position, but positional isomers, we're saying they have the same molecular formula, but different position. What is in a different position? It is the side chain, it is the substituent, and the functional group. I always say SSF so that you always remember that in a positional isomers, we're talking about three things that can be in different position. So it's the same molecular formula, but different position of the side chain, of the substituent, or the functional group. So the functional group can be moving. For example, you can be having an alcohol where you are having now, if I'm to give you an example, where you are having the OH in carbon number 1, and then that will be, if it's 4 carbons like that, that will be butan 1-ol. But we can move the OH to carbon number 2, then it becomes butan 2-ol. So butan 1-ol and butan 2-ol, they are positional isomers. Why? Because they have the same molecular formula but different position of the functional group. So we're saying always remember what is different. It is the side chain, it is the substituent, or the functional group. So very much important there for you to remember. Remember chlorine, we're treating it as a substituent when we're doing our naming. So if you are having 1-chloropentane and 2-chloropentane and 3-chloropentane, you can see that our substituent, which is our chloro, is in carbon number 1, carbon number 2, carbon number 3. So we'll refer to that as a positional isomer because they have the same molecular formula but different position of the substituent. So it's important that you have that understanding about these isomers. The last isomers that we do is the functional isomers. So functional isomers, same, they're isomers, they must be same molecular formula but different functional group. So what is different is the functional group. And we said these are functional isomers. We said we have 4 functional isomers that we know. That is your cake, and your cake, you are saying always remember, we are saying a carboxylic acid and ethers are good examples of functional isomers. And we are saying aldehydes and ketones are functional isomers. So always know that in terms of functional isomers, we're talking about here your cake, we're talking about here your carboxylic acid and esters, and then your aldehyde and ketones as your functional isomer. So I think now you remember all these and you will ensure that in terms of these definitions, in terms of this concept that we discuss on this page, you are able to always remember and be able to write and collect the marks that you're supposed to collect. Now, with no any wasting of time, we want to spend more time with problem solving so that we share with you the skill of how do you solve problems. So let's look at this question, for example, number 1, which says, which one of the following is the general formula? Which one of the following is the general formula? The keyword there is general formula of alkanes. Those are the keywords. So we want general formula of alkanes. And then you will have checked, you know that CnH2n will be general formula for alkenes. CnH2n minus 2 will be general formula for alkynes. At least with this, I'm revising with you the general formulas of these homologous series so that you are able now to always remember the general formula because they are important as well. CnH2n plus 2, where we have maximum number of hydrogens. Definitely, this will be the general formula of alkanes. So remember, alkanes is CnH2n plus 2. However, when you move to alkenes, you're going to remove the 2 hydrogens. Hence, it becomes CnH2n for alkenes. When you move from alkenes to alkynes, you remove another 2 hydrogens. You're going to get CnH2n minus 2. And then when it comes to alcohols, you're just going to replace one on the CnH2n plus 2. You only replace one hydrogen with the OH there. That's why now it becomes CnH2n plus 1 OH. Definitely, that must be the general formula of alcohols. So you are able now to determine the general formulas for these homologous series. I hope that helps you, and you will not forget the importance of knowing the 9 a general formula for the 9 homologous series that we talked about, which we said is AAA, Higg, A, and C, so that you don't forget that you have 9 homologous series, and we are saying for all of them, you must know their general formulas. I've shown you good examples there with those 4, and I know that you will look at all of them, and when you go to the exam room, you must be knowing all the general formulas for all the 9 homologous series. Now, let's go to question 2 there. Question 2 is saying, consider the following statement regarding the compounds in the same homologous series. It's very much important to always highlight the keyword there, same homologous series. So we're talking about organic compounds that are in the same homologous series. So we're saying organic compounds that are in the same homologous series, they have the same boiling point. Let's take one homologous series like alkanes, for example. You will have methane, ethane, propane, butane, pentane. Will they all have the same boiling point? No. As the chain length increases, the boiling point increases as well. So you will definitely know that the first option is not the correct answer. Now let's look at option Roman figure 2 there. It says compounds, always read from the statement, compounds in the same homologous series, they have the same functional group. How did we define homologous series? Because homo means same. We know that homo means same, but we said they have the same general formula. And if they have the same general formula within a homologous series belonging to the same family, they must have the same functional group. Definitely, Roman figure, this number 2 is correct. Let's look at Roman figure 3 there. They are saying compounds in the same homologous series, they have the same molecular formula. No, I've shown you with methane, ethane, propane. When you look at that, they don't have the same molecular formula, but they belong to the same homologous series. So the only option that is correct there is Roman figure 2. Then definitely our answer must be A. You see, when you're answering even multiple choice questions, which you are using here for consolidation, you are able to answer with confidence and knowing that you are answering correctly. Now, question 3 is saying name of the functional group. I'm happy with this slide as well to say you got to know that there are 4 functional groups that we must know them by name. We just don't describe them. We know them by name, and they are given here. And we are saying which one belongs here to the alcohol. So we'll look at all of them, then we'll decide which one is the alcohol. Let's look at the first option, which is option A, carboxyl group. Carboxyl group is a COOH, cool there, the cool there. Remember, when you are writing the structural formula of the functional group, you will show all the bonds around the carbon. So you see there, a carbon is surrounded by 4 bonds around it. That's what you will do. When you're writing that carboxyl group, you will write a C double bond O with an OH, but everything, oxygen must have 2 bonds around it, hydrogen must always have 1. So it's important that you show the correct number of bonds. So what have I done? This is the name of the functional group. This is the structural formula of the functional group. So whether a question comes and say, write down the structural formula of the functional group, you know how to draw it. And then what is the homologous series? What is the homologous series which this one belongs? We know this carboxyl group is for carboxylic acids. Carboxylic acids, they have carboxyl group as their name of their functional group, and the structural formula of the functional group for carboxylic acids is written like that. So you see, the question can come any of those 3, you are able to answer with no problem. Now let's look, which means number A, alphabet A is not the answer to this question, because remember we're looking for the alcohol. Now let's go to B. For B, we're saying carbonyl group. Now let's check what is a carbonyl group. A carbonyl is a C double bond O. In this case, it must be surrounded by 2 carbons. So very much important that the C double bond O must be surrounded by 2 carbons. And each carbon, at all material types, each carbon must be surrounded by 4 bonds around it. And that's how you will write a carbonyl. And then we are saying this carbonyl, where do we find it? We find it in ketones. So important. They say, okay, they give you a ketone, they say write down the structural formula of the functional group. That's how you'll write it. What is the name of the functional group for ketones? Is the carbonyl group. So you know how to draw it, you even know how to write, to name it, because these 4 functional groups have names. Now the formyl group is a C double bond O followed by hydrogen. Where do we get this one? We get it from aldehydes. So the functional group for aldehydes is the formyl group. The name of the functional group for aldehydes is the formyl group. And we are saying you will write it as C double bond O with an H, and always check the number of bonds. So the question can say, draw the structural formula of the functional group, or write the name of the functional group for aldehydes. Definitely you know how to go about it. And then lastly, we have a hydroxyl group. The hydroxyl group is a carbon. The functional group is the carbon that is bonded to the OH. The carbon. So don't make a mistake of writing a hydroxyl group as an OH, because if you say draw the structural formula of the functional group for alcohols and you write OH, you are wrong. It must be a carbon bonded to the OH, and always our number of bonds: hydrogen 1, carbon 2, and carbon 4, and oxygen 2. All make no mistake at all times that your oxygen will have 2 bonds, your hydrogen will have 1, your carbon will have 4. So we are moving like that, and then we are saying this is the hydroxyl group. We find it in alcohols. So we are able to answer the question to say the correct answer is D. Hydroxyl group is the name of the functional group of alcohols. I hope that helps you, and then you build your confidence and you are able to move. Now, which one of the following compound is an aldehyde? Remember the homologous series, they give us the suffix. They give us the suffix to say how will the name end. For aldehydes, the name must end with AL. So you are able to see that pentanal, this must be aldehyde, because it gives us the suffix how the name end. Pentan to all for alcohol. So you know that this one, all is for alcohols, al for aldehyde, and then pentan to own for ketones. So you see the suffix, we're getting it from the homologous series. Ethyl propanoid, This one, the O8 esters, they have O8. Their name will end with O8. You know that is an ester. And then we'll talk about esterification, the process itself, because it's very much important as well for your exams. Now, which one of the following compounds is a carboxylic acid? Which one is a carboxylic acid? We have talked about it. By now you know. But the main issue here, we want you to understand the condensed structural formulas. Because if you are given a structure like that, you must be able to know which homologous series these organic molecules belong to. Let's look at number A. You have a C double bond O surrounded by 2 carbons. Definitely, you will know that this is a ketone. A ketone with 3 carbons. So definitely that must be propan. Propanone. That will be propanone. Remember, you don't have to indicate the position of the functional group of the C double bond O, because there is no positional isomers there. So you just call it propanone. Is fine. You don't have to say propan-2-one, because there is no any other propanone in this world. There's only one propanone. It doesn't have a positional isomer. So you will just refer to it as propanone. You don't have to say propan-2-one. Remember, when you are saying propan-2-one, is because you are different. When you indicate the number, you are differentiating it from another homologous series. Now let's look at number B then. You can see we have a C double bond O and an H at the end. That one for aldehydes. So how many carbons? 1, 2, 3. You will know that this must be propanal. For aldehydes, propanal. So it's important that you understand all the formulas. Remember, we started with the general formula, the molecular formula, and then the structural formula and the condensed. This one is the condensed structural formula. So it's important that you are able to see that. And then the coup there, the C double bond OH. Remember, we only have 2 homologous series that have 2 oxygens, which is our ester and our carboxylic acid. And we know that for carboxylic acid, in carbon number 1, we have the C double bond O and the OH. So the 2 oxygens are in carbon number 1 in terms of carboxylic acid. So you are not confused. You know that when I see 2 oxygen, I will definitely know that is EC. It's either an ester or a carboxylic acid. When I see 2 oxygens within a molecule, I know that it's either an ester or a carboxylic acid. So definitely this is a carboxylic acid. And then for an ester, this 2 carbons, the carbon with the 2 oxygens must be surrounded by 2 carbons around it. So it's easy for you to differentiate between esters and carboxylic acid because of the position of the C double bond O. You know that the C double bond O for carboxylic acid is in carbon number 1, but for an ester, it must be surrounded by other carbons on either side, on the 2 sides. Now, this one is CH3, CH2, CH2, 3 carbons. You see, this is an alcohol with 3 carbons, so that is propan. Where is the alcohol? In carbon number 1, so you will call it propan 1-ol. Why do we call it propan 1-ol? Because if we take the OH to carbon number 2, it will become propan 2-ol. So as long as it is having a positional isomer, we are forced now to indicate the number where we will get our OH in the structure. Now, which one of the following pairs of compounds are functional isomers? Remember, with functional isomers, already I told you that functional isomers, we have cake. We said it's either a carboxylic acid and an ester, or an aldehyde or a ketone. So it's easy for you now to say, okay, do we have aldehydes and we have methanol and methanol? Definitely says no. We have a butane, alkane, and another. These 2, butane and 2-methyl propane. These must be chain isomers. They have different types of chains. You can see this one is unbranched, this one is branched. So this must be chain isomers. And then you have propan 1-ol and propan 2-ol. This must be positional because we are changing the position of the OH there. So this is positional isomers. And then you are having the carboxylic acid and an ester. Oh, from our cake there, you can see these two are functional isomers. So our answer is D. So with that skill, you are able as well to have confidence as you answer questions. Now, consider the following structure. Which one of the following pairs of reactants can be used to prepare this compound in the laboratory? Very important. Which ones can be used to prepare this compound in the lab? So you go to check now to say, okay, let's check how many carbons do we have this side of the oxygen. You can see that we have 1, 2, 3. And this part of the structure that doesn't have a C double bond O is from the alcohol. So you got to see that we had an alcohol with three carbons. And for this type of reactions, mostly we are using our primary alcohols. Definitely this must come from propanol. So you can see that this is from propanol. And on the acid side, the one that comes from the acid, the OH part, which is now O8, this part. And then you are able to see that, okay, this one is a carboxylic acid with 2 carbons. That must be ethanoic acid. And as I indicated, that we use primary alcohols. Definitely this must be propan-1-ol. Propan-1-ol. Remember, it's a primary alcohol. Why are we using? Are we calling the primary alcohol? We're saying the OH or the hydroxyl group is in the carbon that is bonded to the OH is bonded to one other carbon. That's how we define our primary alcohols. We're saying the carbon that is bonded to the OH is bonded to one other carbon. So that's how we are saying this is primary. It is primary because the primary that was bonded to the OH is bonded to one other carbon. If the carbon that is bonded to the OH is bonded to 2 other carbons, we'll call that a secondary alcohol. And if the carbon that is bonded to the OH is bonded to 3 other carbons, we refer to it as a tertiary alcohol. So very much important. So in this case, we have propan-1-ol and ethanoic acid, which in this case, we have ethanoic acid and propan-1-ol, which is option number C. So you are able to choose your answer. Remember here that during esterification, we are using our catalyst as sulfuric acid. And an ester, this we call this propyl ethanoate. So these are 2 names. You don't have to make it 1 name. There must be space between the 2. So it's propyl from the alcohol and ethanoate from the carboxylic acid, ethanoic acid. So this is propyl ethanoate. So you will write the name like that. And this is not the only product that is formed during esterification. Remember, we're having an alcohol reacting with the carboxylic acid to form the ester plus water. So you must always have that in mind to say water as well is an inorganic product that is formed during esterification. So I hope that helps you as you are revising all these topics. Now, the issue of empirical formula, which is the simplest whole number ratio. Empirical formula refer to the simplest whole number ratio. And we are saying which one of the following is the empirical formula of 1,2 dichloroethane. Now, the best thing to do is to first draw the structure so that you can see ethane, and you can see in carbon number 1 we have a chloro, in carbon number 2 we have another chloro. Then you are able to draw it like that. From there, when you are having that structural formula, you can write the molecular formula, which in this case it is C2H4Cl2. And remember, we're saying empirical formula is the simplest whole number ratio, which means we're saying, is there any other number that we can divide here so that we cannot be able to divide this anymore? And if you divide this by 2, you will get CH2Cl. Then that will be the empirical formula, which is the simplest whole number ratio. that we get. In this case, it's CH2Cl, and you can see that in number B. So you're able to see the empirical formula. So I think by now you know the difference. This C2H4Cl2 will be the molecular formula. CH2Cl will be the empirical formula, which is the simplest whole number ratio. Now we move. IUPAC naming, very, very, very important that you have the knowledge of naming organic molecules. This skill you must have at all times. And as discussed, we are saying always we have the prefix. Prefix is from the substituents. Remember the substituents in terms of our syllabus. We are talking about your methyl, which is your CH3. We're talking about your ethyl, which is your CH2, CH3. We're talking about your chloro. We're talking about your bromo. And then iodoate. Sometimes they do ask about it, and your fluoro. So we can't leave them out because we don't know what the paper will have. So you have to know that these are the substituents, which means they belong to the same family called substituents, and there is no preference amongst them. When we are doing naming, we don't prefer any of them because they belong to that one basket called substituents. So don't be confused when you are doing naming. They are all substituents. We'll just check which one comes that you are able to reach faster as you are numbering your structure, and then you prefer in that order. So you will see when we do naming, we are emphasizing that all these are our substituents. And a substituent must always indicate the position of the substituent. So if we have a substituent, you will say 2-chloro if chloro is in carbon number 2. You will say 2-bromo if bromo is in carbon number 2. You will say 2-methyl if methyl is in carbon number 2. You will say 3-ethyl if ethyl is in carbon number 3. So all of these are our substituents, and we're saying they don't go alone, the substituents, they all go with their position to say where do we find them. Where do we find the substituent, which is your ethyl, your methyl, your bromo, your chloro, your fluoro, and your iodo. I think that will help you. Now, we have the parent chain now. The parent chain, which is the root of the structure, we're saying the longest carbon chain. How many carbons do we have on the longest carbon chain? And we are always guided by this to say 1 carbon is mid, 2 carbons is, 3 carbons prop, 4 carbons put, 5 carbons pent, 6 carbons hex, 7 carbons hept, and 8 carbons is oct. So very much important that you always check the longest carbon chain. And learners sometimes they make mistake. If a carbon chain is written like that, they will think that the carbons that are going downwards, they are not part of the longest chain. They are still part of the chain. It's just that this structure is bent. So please, if a structure is this, you must know that all these carbons, they are part of the longest carbon chain. There's no branch there. It's one carbon chain is just bent. If you want, you can write it straight like that so that you see it clearly. So please don't be confused by structures that goes like that. And if you can check there, we're having 1, 2, 3, 4, 5, 6. So you're able to see that this will be a hex. And because there is no any other functional group there except for the carbon-carbon single bonds and carbon-hydrogen bonds, which we use for alkanes, definitely you are going to refer to this one as a hexane. So if you are having a substituent, you will definitely look for the position of that substituent. What am I saying? I'm saying when you are naming, you will always start from here. You will say, what is the suffix? I find it very easy when you do like that to say, what is the functional group? What is the homologous functional group that we find in this structure? And we said it's carbon-carbon single bonds, carbon-hydrogen single bonds. We said, okay, this is an ane. So we know that this is an ane. And then how many carbons in the parent chain? 6. So that will be hex. Remember, for alkanes, we write only for esters and carboxylic acid where we write 2 names. But all the others is 1 name. No matter how long the name is, you will write it as 1. If we have a substituent, for example, I can remove this and put a chloro there. Then I will be able to call this 1, 2, 3. So I'll call this 3-chlorohexane. So always the name is starting with the prefix, which is your chloro, your bromo, your iodo, your fluoro, your methyl, your ethyl. As long as you're having those branches, as long as you are having chloro, bromo, you must always start with them. We refer to them as substituents, and you must always show their position. I hope that helps you as you continue with naming of structure. We're given this structure to name, to say, consider the following structure. Which one of the following is the IUPAC name of the compound? Now, if you look at this compound, very tricky. I told you that sometimes the structure is bent, so you must always be careful of that. Remember, where the functional group will always take precedence, will always get preference in terms of numbering of, say, which one is carbon number one. The carbon number one is this one. Why? Because it is the functional group. What is the functional group? We said this one is the carboxyl group. The name of that functional group, we said, is the carboxyl group. Where do we find carboxyl group? In carboxylic acid. So we know, we are deciding that we first look for the functional group, and then the functional group tells us about the homologous series to say this is a carboxyl group and this must be carboxylic acid. So we have our carboxylic acid there, and then you are able now to do the numbering of the longest carbon chain, which can be 1, 2, 3. You have an option to go to the left or to the right. Is the same, doesn't matter, because the chain is the same. It's only one carbon on the left and the right, but the structure doesn't end up there. The structure ends, you can end it on the left or on the right, is still the same. I chose to go that route. So you're able to see that this is 1, 2, 3, 4. And you know that 4 is butan. 4 is butan. 4 carbons is butan. And then because it's a carboxylic acid, it's a butanoic acid. So you see the functional group is saying this is an oic acid. The parent is saying 4 carbons, hence we're having butan there. Do we have any substituents? Yes, let's go and check where do we find the substituents. In carbon number 2, we find 2 substituents in carbon number 2. 1, 2. In carbon number 3, there is another substituent. So our substituents are the same. So we can now just call them 2.2 because in carbon number 2, we have 2 of them. So it's 2, 2, 3. So you are able to see that this must be 2, 2, 3. How many are they? There are 3. So this must be tri. And you see, I'm writing a comma between the numbers, the like terms. Like when I have the same, I just write a comma. But now same numbers, 2, 2, 3. But when I have a number and an alphabet, unlike terms, for you to remember, I will use a hyphen there to say this is tri what? Methyl. We have 3 methyls there. So the name of this one will be 2, 2, 3 trimethyl butanoic acid. And then you just go and check the 2, 2. Don't make a mistake, it's 2, 2, 3. I think I've added 2, 2, 2, 2, 3 trimethyl butanoic acid. Then you're able to write it there. Don't be confused. And then you are able to choose your correct answer with no problem. Now let's move. I think those activities help you. As I consolidate this one, this is most of the time you are getting our question 2 that looks like this one. To say now, when you get this one, what do you do? How do you go about doing it? 100% you will always, hence I wrote here FH Jameson, for you to always remember that you must first look for the functional group. To say what is the functional group there, you can see that there is no any other functional group. Then this will be is carbon carbon single single bonds, carbon hydrogen single bonds. This must be an ane. This must be an ane, and then that is means now alkanes. And then you check in how many carbons do we have in the longest carbon chain. So we'll be having 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, number from anywhere is still fine. So you're having 6. So you know that this must be hexane. This must be hexane. Do we have substituents? Yes. Which one now is the take preference? Look, in this one is competing to be carbon number 1, as well as this one as well, competing to be carbon number 1. So I cannot decide based on these 2 terminal carbons, the first carbons on the left and on the right. I can't decide which one is carbon number 1. I must go to the next one. Let's go to the next carbon. We have a substituent called bromo. We have another substituent called methyl. So you see, they are all my substituents. So I told you about the issue of preference to say they belong to the same family. We don't prefer between a methyl and a bromo. So I must continue with my journey. Maybe something will help me to make a decision because I don't know who to favor. I don't know who to prefer between bromo and methyl. Let's go to the next carbon. What do we get? We get a methyl in carbon number 3 from this side. Carbon number 3 from this side, there is nothing. There is only hydrogens. So I'm going to prefer the left-hand side because it's the mostly substituted side. So when I say now, this is carbon number 1, number 2, number 3, number 4, number 5, number 6, you will understand me. I don't hate bromo, but I'm saying that on the left, I have many substituents. So always when I'm preferring, I will prefer where the mostly substituted side. So I will prefer the left. Hence, when I'm numbering, I will number like that. Now, when it comes to naming, remember we said this is hexane. Now I will check, okay? In carbon number 5, we have a bromo. In carbon number 2, let me write what we have. In carbon number 2 and number 3, we have dimethyl. Because there are two, we say dimethyl. Don't forget, like terms is a comma, number, comma, and then when it's alphabetic number, hyphen. Don't forget that. We penalize you if you don't do that. So we're saying 2,3 dimethyl. In carbon number 5, we have a bromo, so it's 5 bromo. And then we have hexane as the longest carbon chain. So when you write the name now, very much important, you are going to use always for writing the name, not for numbering. For writing the name, always you will use alphabetical preference amongst your substituent. So in this case, I will give the name of the structure as 5-bromo because B comes before M for methyl. So this is 5-bromo 2, 3 dimethyl. Don't forget the hyphens. Dimethyl hexane. Don't forget the hyphens between the number in alphabets and the comma between the number and the number. Then we name that structure well. So always have that in mind. And I'm saying for each one, know the general formula, molecular formula, structural formula, condensed structural formula, isomers, as well as the name, IUPAC naming, to say how do we name the structure. So when you are given a molecular formula like that, you will first draw it so that you can see what is happening. It's very difficult for you now to know whether that is an aldehyde or an alcohol. But immediately you start to draw that structure, you will be able to see that you have 3 carbons and then you have 8 hydrogens. So it's 1, 2, 3, 4, 5, 6, 7, and you are left with 1 oxygen and 1 hydrogen. So you're forced to say and then OH there. So you're able to see that, oh, this must be an alcohol. So if you don't draw it, you won't know. You might make a mistake of thinking that it's an aldehyde or something. So hence I'm saying when you're given molecular formula, draw structural formula. You want to see things clearly so that you can make decisions that are informed. For example, then you are given pentan to own, draw it. And then the 2-on is showing you the position of our functional group to say, okay, in carbon number 2, we have the C double bond O. So you will draw the 5 carbons, and then you will be able to show that in carbon number 2, we have C double bond O. And then don't leave your structure like that because we always penalize you if you don't show all the hydrogens in the structure. So pentan to O. So you're able to do that. We can ask you what will be the functional, the functional isomer of pentan to O. So you will know that pentanal will be the functional isomer because you see aldehydes and ketones, they are functional isomer. So all that, and I'm hoping that any question that we'll get out of this, you are able to do with all the foundation that we've laid. Now, if I don't waste time, I want to talk physical properties. Physical properties as indicated to say under physical properties, we don't do much. We're talking melting point. We're talking here vapor pressure. We're talking here boiling point. I have my reasons why I'm arranging them like that. Because we are having a melting point. We're saying melting point is not a point. This one, you got to get it. Remember, when you do acids and bases, you have equivalence point and you have end point. and all those we refer to them as points. But these ones, they are not points. They are melting point is a temperature. It's not a point. It's a temperature at which the solid phase and the liquid phase are at equilibrium. We'll write it in full. The temperature at which the solid phase and the liquid phase are at equilibrium. And then what is the vapor pressure? We're saying the vapor pressure is the pressure exerted by vapor. Pressure exerted, you see, I'm just switching them like that to say it's a pressure exerted by vapor at equilibrium with its liquid in a closed system. Please don't forget to say in a closed system when you're defining vapor pressure, because if the system is not closed, we won't reach equilibrium. For the second equilibrium, for the first one, remember the water is solid, so it's isolated. There's nothing that is coming in or going out. Hence, we don't say in a closed system. So remember, we're saying melting point is the temperature at which the solid phase and the liquid phase are at equilibrium. And the vapor pressure, we're saying, is the pressure exerted by vapor at equilibrium with its liquid in a closed system. Now we have what we refer to as boiling point. Boiling point as well is not a point. It's a what? It's a temperature at which the vapor pressure is equals to the atmospheric pressure. Don't make a mistake of saying the atmospheric pressure is equals to the vapor pressure. No, it is the vapor pressure that increases until it is equals to the atmospheric pressure. Remember, atmospheric pressure above sea level here is 101.3 kilopascal, what you call 1 atm. So it is the temperature at which vapor pressure is equals to atmospheric pressure. And those are the three physical properties that we do. And we are simply saying now, these physical properties now, this is what we are measuring here. This is our dependent variable. So look at this question as a question on an investigation or an experiment where the dependent variable, it is your melting point, your vapor pressure, and your boiling point. And I'm saying here for you now that let's look at our independent variable. What is that which we can change in order for us to change the melting point, the vapor pressure, and the boiling point? Because these ones were saying they are dependent. So these ones are dependent variables. What are the independent variables? I want to come here and write our independent variables, or what do we change in the structures? According to our exam guideline, we change the intermolecular force by changing the functional group. So we have the intermolecular force, we have the functional group. So when you change the functional group, we're changing the intermolecular force in our case. And then so it's the intermolecular force, the functional group, and then the chain length. So the chain length and the branches. So those are the three things that you can change, because if you change functional group, in our case for grade 12, you are changing the intermolecular force, and then you are having the chain length. You can change the chain length and change the branch. And if we change those three, we are able to answer all our questions. So it means when you get your question, you will always check your independent variable and your dependent variable. At least the dependent, already you know them, is melting point, vapor pressure, and boiling point. So you just check what are we measuring in this experiment. Then you know that that is your dependent variable, what we are measuring. What are we changing? We are saying we change the intermolecular forces, we change the functional groups, we change the chain length and the branch. Those are the three things that we change within a structure. So have that as we go to this question, we won't have a problem. Now you will know that we always put our dependent variables this side and our independent variables, what we're changing. In this case, is the number of carbons, which means we're changing the chain length. The chain length is changing. So you can see that as the chain length increases, you can see what is happening to the boiling point. As the chain length increases, the boiling point as well is doing the changing. You will see as we do the questions. So you will get the question in a graph form, the way I gave it like that, or you will get your question in a table form like that. And then we are saying that always know. If you look here, check what is changing, because already you know your dependent variable is your vapor pressure, which is your physical property. which is a vapor pressure. That is what we are measuring. We are measuring vapor pressure. But what are we changing? Which is your independent variable. Always have that information to say, okay, in this one, if we check, we have 1, 2, 3, 4, 5 carbons, we have pentane, we have 2-methyl butane, we have 2,2 dimethyl propane. So you can see that we are changing the branches. 0 branch, 1 branch, 2 branches. So you can see that, okay, as we increase the number of branches, what is happening to the vapor pressure? So you can see that the vapor pressure increases with increase in the number of branches. When you increase the number of branches, the vapor pressure increases. What does that mean to us? It means that as we increase the number of branches, the strength of intermolecular force is decreasing. And as the strength of intermolecular force decreases, less energy will be required to overcome the intermolecular force. Therefore, they will have more vapor that is formed. So it means when the strength of intermolecular force is the weakest, that's when we have the highest vapor pressure. Highest vapor pressure, meaning that we have the lowest, the one with the lowest boiling point has the highest vapor pressure, which means in this case, this one has the highest vapor pressure, which means in terms of boiling point, this one will have the lowest boiling point. And this one will have the highest boiling point. So have that in your mind to say, this is the relationship in terms of boiling point, vapor pressure, and melting point. Now, how do I go about answering these questions? So we are saying when you're answering these questions, the first thing that will always look is the difference in structure. I already indicated that I'm expecting you to look for 3 things: to look for the chain length, to look for the branch, to look for the change in the functional group. Already I told you that when you change this functional group, we're changing the intermolecular forces. So you'll always check in the structure what is changing. Then you answer the question based on what is changing, your independent variable, because we are always looking at the relationship between the independent variable and the dependent. How is the change in the independent variable affecting the dependent variable? As the chain length increases, the boiling point increases. You see, always the boiling point is depending on the chain length. As we increase the chain length, the boiling point increase. As we decrease the chain length, the boiling point decrease. Same with melting point. However, when it comes to vapor pressure, we're saying as you increase the chain length, you are going to expect that the vapor pressure will decrease. So that is the only difference in terms of vapor pressure. So the first thing, you'll say what is changing or what is the difference in structure. Number 2, you'll state the effect of this factor on the intermolecular forces. So does the change in chain length increase or decrease the strength of intermolecular force? What is the effect of increasing the number of branches? As you have seen that as we increase the number of branches, the strength of intermolecular force decreases. That's what we're talking about. And then what is the energy required, energy needed to overcome intermolecular force? So definitely when the strength is increasing, you know that more energy will be required to overcome the intermolecular force. I want us to practice this in a question so that you are able to answer the question. Now, this one is saying, which one of the following compounds will have the lowest boiling point? Which one will have the lowest boiling point? Remember, lowest boiling point, we are saying lowest strength in terms of intermolecular force. So you can just group them to say, okay, you have the understanding, alkanes, they have London forces. Aldehydes, butanol, they have London forces and dipole. So you will always refer to the highest strength, the highest force that they have, which is dipole forces. And then butan 1-ol has one side of hydrogen bonding. So this one is a hydrogen bonding. And then methyl propane, like butane, it will have London force. But compared to butane, methyl propane will have a less strength of intermolecular force. Why lower strength of intermolecular force? Because it has a branch. Immediately when you increase the branches, you are decreasing the strength of intermolecular force. So you are able to see it like that. So we are saying which one of the following compounds will have the lowest boiling point? Oh, this one, highest, because it has all the three. It has London forces, it has dipole, and hydrogen bond. And hydrogen bond is the strongest of all of them. So butanol is not the lowest, it's the is the highest. It will have the highest, followed by butanol with dipole, followed by London forces, and the lowest will be methyl propane because it has London force same as butane, but methyl propane has a branch. So as a branch, further when you increase the number of branches, you are further decreasing the strength of intermolecular force. So definitely T will have the lowest in strength of intermolecular force. The relationship between boiling point and number of carbons in a straight chain molecules of aldehydes. So we're looking at aldehydes, alkanes, and primary alcohols. I always want to say this to learners to say immediately when you are given three homologous series like that, just arrange them in terms of increasing or decreasing strength of intermolecular force. What do I mean? I mean you have alkanes, you have aldehyde, you have primary alcohols. You can simply say, okay, alkanes, they are the weakest because they are having London forces. And then we are having, followed by aldehydes because they have dipole, followed by alcohols. Alcohols, they have hydrogen bonds, so they are stronger than the others, they are the strongest. And then hence you will see that the one with the strongest would be A there. And then the question is saying which compounds are represented by curve B. Curve B, you can see that it's in the middle there. It's not the strongest. The strongest is A, the weakest is C. So you can see that aldehyde is the one in the middle there, and you're able to choose your answer, which is C. Now, a structured question, define the term boiling point. So you are able now to define the term boiling point. Remember what we said, it's not a point, it's a temperature at which the vapor pressure is equals to the atmospheric pressure. What is the relationship between the strength of intermolecular forces and boiling point? We talked about this one to say as the strength of intermolecular force increases, the boiling point increases. You cannot say directly proportional. We don't use that here in paper 2. We say now as the strength as the strength of intermolecular force increases, the boiling point increases, not directly proportional. We use that nicely in paper 1, it works well. But here, let's stick with increasing the strength of intermolecular force, increase with the boiling point will increase as well. The relationship between the strength of intermolecular force and boiling point is investigated using 4 organic compounds. So we're given 4 organic compounds, A, B, C, D. I would like to advise you here that when you're given compounds as A, B, C, D, propane, propan-2-one, propan-1-ol, and propanoic acid, when you write, it's better to talk about A, B, C, D than having to talk about the entire structure because sometimes it becomes too much. So I find it easier to talk about compound A, compound B, compound C, compound D because they are given there. Now refer to the type. The question is channeling you to say when you answer, refer to the type and strength of intermolecular forces to explain the difference in boiling point between compound A and B. Now, if you check compound A and B, the type for compound A, propane, we said is London forces. For propanone is dipole. So you will first write the intermolecular forces that we get to say A has London forces, B has dipole. Now the second thing, you talk to the strength of intermolecular force. Definitely B has stronger intermolecular force than A. You see the importance of B and A now. B has stronger intermolecular forces than A. And then the one that has strong intermolecular forces, we are saying more energy will be required to overcome the intermolecular forces in B than in A. So you are able to answer in that way and you will get your 3 marks. When it comes to 3.3.2, compound C and D, we are saying now for compound C and D, we are talking about an alcohol and carboxylic acid. Those are relatives, remember, because we are saying an alcohol has one side of hydrogen bond and a carboxylic acid has 2 sides. So definitely by merely mentioning that, you can see that the other one is able to form 2 hydrogen bonds, the other one. So you are able to see that, okay, now you will write that between compound C and D, we are comparing the boiling point. So we're saying Propanoic acid, which is D, D has higher boiling point. Why? Because D has two sides of hydrogen bond, and then you are saying C has one side of hydrogen bond. So that's the first mark that you will say. And then the one with two sides has stronger intermolecular force than D, has stronger intermolecular force than C. The third mark, you are saying more energy will be required to overcome intermolecular forces in D than in C. So with that, you are able to answer your question. Is compound B a gas or a liquid at room temperature? Remember, room temperature, Lenas, is 25 degrees Celsius. So they are saying go to B, which boils at 56. So you can see that it hasn't boiled yet because room temperature is 25 degrees Celsius. So definitely it's not a gas. It's not a gas because it can only become a gas after boiling. So you know that if it's not a gas, it is a liquid. So you know that compound B is a liquid at room temperature. What is the reason? 56. Its boiling point to only boil at 56, and room temperature was still at 25. We haven't reached the 56 degrees Celsius. That is your 10 mark, and you are able to do that. And with now wasting of time, we'll move to organic reactions. Now, on organic reactions, we are saying now, as I indicated to you, that we are doing addition, we are doing a substitution, we are doing elimination, we are doing oxidation. Sometimes we are referring to it as combustion, and then we are doing esterification. So those are the 5 that we do. Remember, under elimination, we have what is called cracking as well, which is the breaking down of large organic molecules into smaller, most useful ones. You can't go to write exam without knowing how to define cracking. Now, we are saying USA, these acronyms, always remember them. To say USA, we're saying unsaturated becoming saturated. So when you're having a double bond becoming a single bond, that reaction is called addition. So when you see a double bond, you know that a double bond can only undergo one reaction in terms of our syllabus, and that reaction is addition, which means USA unsaturated, which is in this case a double bond, becoming saturated, which is our single bond. The reaction is called addition. And you have SU. SU stands for when you have saturated becoming unsaturated, we call the reaction elimination, which means the formation of double bonds. In our case, it is our elimination reactions. Sorry, when you have saturated forming other saturated compounds, the reaction is called substitution. So you got to have that. And we are saying CEDS, which stands for concentrated, is for elimination, and dilute. So when we are using concentrated sodium hydroxide, concentrated strong base, you know that we are going to eliminate. But when we use dilute sodium hydroxide, we are going to, the reaction that we are talking about is substitution. In this case, it will be hydrolysis. So you got to have an understanding of saying CDS. It makes you remember this acronym to say, once I use concentrated sodium hydroxide, I'm eliminating. But once I use dilute sodium hydroxide, I am substituting. And then this was the question that learners were asked 2021 to say too many learners did not attempt this question at all. This question, learners were given butene, they were given compound A, compound B, and 1,2 dibromo propane. And what learners didn't see here was that this reaction here that took place here is cracking. Remember, the cracking in our syllabus were cracking alkanes. It's alkanes, we break down larger alkanes into smaller, most useful ones. So in this case, we had butene, and for it to become an alkane, it must become an alkane so that it can undergo cracking. So it's important that here it means we have added hydrogen. And when we add hydrogen, we are saying the reaction condition, we use platinum, palladium, or nickel. So we can use those catalysts. So always all the reactions, you must know their reaction conditions. So we have butene forming butane. And when you have butane, it can undergo cracking. And when you say cracking, cracking forms alkene plus alkane. That's what cracking does. It forms an alkene plus alkane, or an alkene plus hydrogen. In this case, alkane is methane, so we know that the other one must be propene. it must be propene. So it's propene plus methane that we formed here. Methane there, we showed it for you there, that we have CH4 that is formed. So this must be cracking. And then when you have propene, you know it undergoes addition. So you can add Br2 there. Immediately when you add Br2, we are going to get 1,2 dibromopropane. So learn and practice many synthesis reaction, this type of reactions where you are synthesizing and then you're going to form something from something. And then I find them very interesting. And we're saying always know the reaction conditions of these reactions. Now, with no wasting of time, we're able to move as well now. To say now, let's look at activity 4. It's saying compound P is used as a starting reactant in each of the two reactions as shown in the flow diagram below. And then we're having compound compound P there. And we are saying this is used as a starting reactant. It's used as a starting reactant. It's used as a starting reactant in each of the two reactions as shown in the flow diagram below. You can see now we're starting there with compound P, which in this case you can see that is C5H11Br. Now, I always say to the learners, it's important that you analyze your question. Look at what is formed when you use dilute sodium hydroxide. Remember what we said, CEDS. When you use dilute, we said the reaction would be substitution. Dilute strong base. So you know that reaction number 1 must be substitution. What do we substitute? We're having a BR, we call it a living group. It's the one that you can substitute. You can see where there is BR. Now we have OL, which is an alcohol, which means we're going to substitute OH, bromo, BR with OH to get that one. But I'm interested mostly on the product that is formed. It's 2-methyl butan 1-on. That tells you that C5H11Br has a branch. So it cannot be 1-bromopentane. It cannot be pentane because it has a branch there. So it means now it must be there is a 2-methyl there and there is a bromo there. So you will see that you're having a 1-bromo. For example, if you look there, you will be having a bromo, and then you are having 4 carbons, which 1-bromo, and then you're having a methyl, say 2-methyl. Then you are having butane, like that. So you are able to see now that that structure that was given there, it can only be 1-bromo without knowing the position. It can be 1-bromo, 2-methyl butane, or 2-bromo, 2-methyl butane. But it cannot be 1-bromo or bromopentane because of what is forming there. So it's very much important that you look at other products that are formed, because it's telling you where I'm coming from. There is a 2-methyl, there's a methyl group in carbon number 2. So the longest carbon chain is not 5 carbons here, it is 4 carbons. That is the thing that I found that it was a challenge for learners. Now, when we use concentrated, we said CEDS. We know this concentrated is for elimination. So here we're eliminating, and there we are substituting. So you can see that this is now hydrolysis. The type of substitution is hydrolysis. We use dilute sodium hydroxide and mild heat. Remember, for substitution we are using mild heat, but for elimination we are using heat. So we use heat here, we heat, but here the heat is mild. So the conditions are important. And then you can see that when we eliminate, we'll have a double bond. We can add HBr, which is your hydrohalogenation. So you are able to analyze that and see all the reactions like that. And then the name of the type of reaction by 1, we said, is substitution because we're using dilute sodium hydroxide. And then is methyl butan 1-on a primary, secondary, or tertiary alcohol? So you can see that the 1-ol there, in terms of the OH, the carbon which it is bonded to is a primary carbon, because that is the carbon atom bonded to the OH is bonded to only one other carbon. How many other carbons? One other carbon. So we're calling it primary alcohol. Write down the structural formula of compound P. So you must be able to write the structural formula of compound P, and then you are led by that one, which is 2-methyl butan 1-ol, and then you are just putting in carbon number 1, you are having the bromo there. Then you are able to see, to show your bromo in that carbon. Then you'll get 1 mark for your bromo, 1 mark for the substituent, and 1 mark for the whole structure. So it's important that you are able to draw the entire structure. Even if you were to lose marks, but you won't lose marks, you know it's butan 1-ol here. So you know that here you have 4 carbons in the longest chain. So you will definitely get a 1 mark for identifying that. You will get another mark for seeing that in carbon number 2, we have a methyl. And then the last mark is for the to see that we have bromo in that carbon, and then that becomes your structure. So I hope you got that, and it will be able to help you. Name the type of reaction represented by 2. Remember, we said concentrated is for elimination. Definitely, this must be elimination. The type of reaction is elimination. Or you can just say dehydrohalogenation will take the answer, or dehydrobromation. But the type of reaction is elimination. The type of elimination is what we are removing, which is dehydrohalogenation or dehydrobromination. To which homologous series does compound Q belong? Definitely, because we are eliminating, we are forming unsaturated, so it must be an alkene. Now, we are able to move on with the question. Name the type of reaction represented by reaction 3. So you can see that as long as you're having a double bond there, you're having an alkene. It must be addition reaction. It must be addition reaction because you are having an alkene there. Now, write down the IUPAC name of compound R. So now remember, you had an alkene here with a 2 in carbon number 2, you had a methyl and you had a double bond. Then you have to write the name of the structure, which is 2-bromo 2-methyl butane, after you have added. So at the end of the day, that is what you will be having. Now, with no waste of time, we can look at cracking. Remember what I said about cracking, to say this is a chemical process in which longer chain hydrocarbons molecules are broken down to shorter, more useful molecules. And they were saying this cracking, it can be thermal cracking, where we are using high temperature and high pressure, or it can be catalytic cracking, where we are using the catalyst. Now, in terms of alkene, I told you that our cracking, it forms alkane and an alkene, or an alkene and a hydrogen. For example, we're given there ethane. It can undergo cracking, elimination, where we are eliminating hydrogen, dehydrogenation, and then it will form an alkene and hydrogen. But look, when you're having butane, for example, you can eliminate the first carbon, then you'll get methane and propene. So always alkane, alkene. We can even go and crack it in the middle, then we'll get you'll get ethene and ethane. And then as well, you can go and remove only the hydrogens, and then you get butene, in there, and hydrogen. So always know that as long as it's cracking, you can crack the structure. It can be 1 carbon, 2 carbons, 3 carbons, depending on what you are doing. But at the end of the day, what is on the left is the same as what is on the right hand side, is equals to what is in the product side when you check the number of carbons and hydrogens. So remember that as always. Now, the last reaction, as we leave the reactions now, is combustion. And then we are saying combustion, which is oxidation reactions. We are saying is the reaction of alkanes like C4H10 when it's reacting with oxygen. So if I can move like that, sorry for that, to say you are having your butane, which is C4H10, and then it's reacting with oxygen to form carbon dioxide plus water. Before you do anything, already you have a mark for reactants and products. You are left with 1 mark for balancing the reaction. And we are simply saying that now, if you come here and say this is N plus 1, at least you are going somewhere, and you can put before the O2 there, you can say 3N plus 1 over 2, just before O2, you can put that. And then you are able to balance the whole reaction. If we do like that, and you say NCO2 plus N plus 1 water. and then N is the number of carbons. So you're simply saying, okay, C4H10 plus N is 4. 3 times 4 plus 1 gives you 13. So you're able to get 13 over 2. O2 gives us N is 4. CO2. N plus 1 is 4 plus 1, which is 5. Water. And then you multiply the entire equation by 2 to get 2C4H10 plus 13O2, forming 8 carbon dioxide plus 10 water. And then that's it. And then you are able to balance that reaction. So it's very much important that you are able to write a balanced equation. Don't forget, this is energy is given out. So energy is one of the product as well. So as you balance those reactions. So please practice combustion so that any question that comes under this reaction, oxidation, you are able to answer. Now, I wanted us to look at the empirical formula as well, to say empirical formula and molecular formula. Last year, there were questions based on this one. And then here we're saying you can be given the mass or the percentage. What you have to do is to convert your mass or your percent to moles. After you have done that, you must divide all the mole values by the smallest mole. You divide all the moles that you got by the smallest mole. After that, you round or multiply to get whole numbers. Remember, empirical formula we are saying is the simplest whole number ratio, the simplest whole number ratio that we are having. That is your empirical formula. And then if molar mass is given, you can be able to determine the molecular formula. How do you do that? You will take the molar mass, you divide it by empirical formula. The empirical formula that you got, you divide it, its mass, the mass of your empirical formula, you take the molar mass that is given, you divide by the empirical formula mass. So I felt that it's important that we demonstrate this one using an example. And even last year we had a question that was based on this one. I find it good that even in the marking guideline we had a table like this, hence using a table is user friendly. To say, you will say we're having carbon, hydrogen, and oxygen. And when we're having those, we're given the mass, so we're saying percentage by mass. So percentage by mass, that must be 100 gram. Our 100% is our 100 gram. Then you write the percentages by mass, which is 72.04 grams, 10.42 grams, 27.54 grams. Then you divide them by, so you are having the mass, then you list their molar mass to say what is the molar mass of carbon is 12. Molar mass of hydrogen 1 or 1.008. Molar mass of oxygen 16. So you are able now to say, okay, I'm having the mass, I'm having the molar mass, I can calculate the number of moles. How do I do that? I will say mass over molar mass. So you will take your mass, 62.04 divided by molar mass is 2, and then you get 5.17. You take 10.42 divided by 1, you get 10.42. You take your 27.54 divided by 16, you got your 1.72. And the next step was to divide by the smallest number of moles, which is 1.72. And when you divide, you will get 1, you will get 3, and 3. You'll get 6 here. Sorry for that. You'll get 6 here, and you get your 3 there. Then you are able to see that you are getting 361 as your empirical formula. So as you write your empirical formula, you say C3H6O. Oxygen is only 1, H is 6, carbon is 3. That is your empirical formula. Now you are able to move from empirical formula to molecular formula if you are given the molar mass. The molar mass was given as 116. So we have our molar mass as 116. So what we will just do, you get the ratio of the molar mass and the empirical formula mass. So once you take the molar mass, you divide it by empirical formula mass, you are able to get your N, which is your ratio between those two. In this case, when you do that, you'll say 116, which is your molar mass, by your empirical formula mass, you get 2. So you multiply N by your empirical formula. You take your empirical formula, you multiply it by N, which is the ratio of your molar mass and your empirical formula mass, which in this case it was 2. So when you multiply this by 2, you get C6H12O2, which is hexanoic acid. So you are able to do that, and it's important that you know this. Remember, we are having half of the paper which is organic, a lot of marks from organic. So we are saying spend time there and remember that. Now, when I move, we look at the basic stoichiometric calculations to say this is very much important now because learners lose marks in terms of this one. To say when I'm given mass, I must be able to calculate the number of moles. That is the simple task that we are asking of you. To say if you are given mass, you must be able to calculate the number of moles. If you are given volume under standard conditions, STP, standard temperature and pressure, which in this case the temperature of 0 degrees Celsius and pressure of 101.3 kilopascals, you must be able to utilize that formula of N equals to V over Vm. And then you are able to use the molar volume of 22.4. Sometimes you'll be given a molar volume maybe of 24, which is at room temperature. Still, you can calculate, use N equals to V over Vm using that molar volume that you are given. But at different temperature, the molar volume won't be 22.4. For example, it's only 22.4 at temperature of 0 degrees or a temperature of 273 kelvins. Now, at room temperature, which is 298 kelvins, you'll find that your molar volume is 24 cubic decimeter so per mole. So it's important that you always have that information in your mind. Sometimes you'll be given the particles, you must be able to calculate the number of moles. Or sometimes you'll be given the concentration and volume, you must be able to calculate the number of moles. So we're saying, know that whatever you are given, the only bridge for you, because if, for example, we gave you A plus B forming C. So the main thing, if now we give you the mass of A, which is solid, for example, we give you the mass of A, you must be able to calculate the number of moles of A. And because it's only when you have the number of moles that you can be able to move from this one to the other one using the mole ratio. So the only bridge between this A and this one is the mole ratio. So it's important that when you are given the mass, you are able to calculate the number of moles. When you have the number of moles, use the mole ratio to determine the other given, can be reactants or products that you are given. So that's what we are saying, to say always check, but the only way of moving from A to B is through the mole ratio. Mole ratio will help us to use information of A in order for us to get B. So we're saying get the number of moles. After getting the number of moles, be able now to determine the unknown using the mole ratio. So that's what we are doing. And we're saying as you write your papers, always think about the mole ratio as it is important. The other thing that I didn't want to leave out is the issue of percentage purity. To say percentage purity, important as well. We are saying here is the total mass of the pure substance divided by the total mass of the impure substance, which is the pure mass divided by impure mass times 100. That's how you calculate the percentage purity. In this case, we're given the total impure as 5 grams of sodium carbonate, and we find that the pure of sodium carbonate was 4.25, and the question was calculate percentage purity, which in that case, you will simply say pure mass divided by total impure multiplied by 100, and then you are able to get your percentage. So if you find a question that talks to the percentage purity, definitely you must do it. Now, let's look at rates of fractions. To say, when it comes to rates of fractions, the first thing that we always emphasizing is the definition of rate of reactions. To say, rate of reaction is the change in concentration of reactants or products per unit time. Please always get the definition correct. And we are saying that now you are able to know the graph of reactants and the graph of products. The graph of reactants and the graph of product, you are able to differentiate between them, because we are saying as we start the reaction, we have reactants only. So the reactants would always start with something, but with the products, we're starting from 0 because we don't have products there. Hence, the graphs that are moving like that, you will see that these are the graphs of the products, and the graphs that are decreasing are the graphs of reactants. And how do we collect our volume, our gas? We're using the gas syringe. Hence, we are saying if this is the graph of the volume of gas, which in this case is H2, is a product, it will start from 0 and it increases until when the curve flattens, we're saying the reaction has reached completion or the reaction has stopped. So have that in your mind. Now, remember we said there are factors that affect the rate of reaction, and those factors, which is temperature, concentration, surface area, nature of reactants, catalyst, and pressure. 6 of them. Always remember how they affect the rate of reaction. So we're saying as for the fastest reaction, the curve becomes more steeper. So you have the steeper the line, the greater the reaction rate. So if you are given a curve, the green one, and we say draw the curve when the temperature is increased, obviously the curve must become more steeper to show that we have increased. When the graph becomes more steeper, we're saying we have increased the rate of reaction. So the faster reaction, which is this one now, it will be able to, it becomes horizontal sooner. So you can see that it's horizontal from there. So it means that the reaction reaches completion faster than the one where the factor was not increased. So this graph, you can use it to show the effect of increasing temperature, effect of increasing concentration, effect of increasing surface area. All those will increase the rate of direction, meaning that the graph will become more steeper, and then when it becomes more steeper, it will be more horizontal sooner to show that it completes faster. But in terms of the volume of gas produced, you can see that it is the same amount of gas produced. Now, when it comes to collision theory, remember with collision theory, we are focusing on this one to say the collision theory says there are 3 conditions that must be met for a reaction to occur. We're saying the reactants must be able to collide effectively with one another, and we're saying these reactants must have enough kinetic energy, and they must have correct orientation. So it's 3 things that I'm looking at there to say the reactants must collide, they must collide with enough kinetic energy, and they must have correct orientation. If we have that, the reaction now will be effective. We'll have effective collision. What is effective collision? We're saying this is the collision that leads to the formation of products. Now, we look at the Maxwell-Boltzmann distribution curves. Very much important that you understand all of them. Now, know that for temperature, when we increase temperature, you see what happens to the graph. It shifts. The graph shifts to the right and touches the original graph. So it shifts to the right, T2. It shifts to the right. Hence, we're saying the graph has dropped. It shifts and then it touches the other graph. It shifts and touches. That is the graph of temperature. And then what do we say when we say use collision theory to explain the effect of increasing temperature? We're saying increasing temperature increase the average kinetic energy of particles. It increases the average kinetic energy of particles. And then we're saying when we so doing, we're going to have more particles with more effective collision per unit time. More effective collision per unit time. You can't write MECPOT. I'm just saying it so that you are able to remember how easy to write it, to say, okay, the first bullet, we said when we increase temperature, we increase the average kinetic energy of the particles. The second bullet, remember we're using bullets. The second bullet, we're saying more effective collision per unit time in full. And then you are able to say we're going to increase the rate of reaction. You can say we'll have more particles with kinetic energy greater or equals to activation energy. So those bullets, please make sure that you are able to show all of them to say when we increase temperature, we increase the average kinetic energy of particles, more effective in full, more effective collision per unit time. It's a 6-letter word. We're emphasizing that. And we are saying you will increase the rate of reaction. We'll have more particles with kinetic energy that is equal, greater, or equals to activation energy. Everything written in full there, you are able to collect your marks. That's how you will deal with increasing temperature under collision theory using Maxwell-Boltzmann distribution curve. Now, if we look at the graph of concentration, it now becomes, it is on top of the original graph, because when we increase concentration from here, concentration is N over V. So when we increase concentration, we're increasing the number of particles. When we increase concentration, we're increasing the number of particles per unit volume. So that is the first bullet. You will say increase in concentration, increase the number of particles per unit volume. It increases the number of particles, which is that N. It increases the number of particles per unit volume. Don't forget. And then what is bullet number 2? More effective collision per unit time, which I said MECPUT for you to remember, but it's just an acronym. You must write it in full to say more effective collision per unit time. Bullet number 3, we said, okay, now we're going to have increase in the rate of reaction. And then you can see here, we still have more particles with energy or kinetic energy greater or equals to activation energy. So you can see that you can follow that order, and then the conclusion is always that it will increase the rate of reaction. But when we add a catalyst, remember what a catalyst does? It lowers, it provides, catalysts provide an alternate pathway, provides an alternate pathway of lower activation energy. It provides an alternate pathway of lower activation energy. That's what your catalyst will do. And then it will have more effective collision per unit time. That one will always be there for all of them. More effective collision per unit time in full. You write it, more effective collision per unit time. And then we're going to increase the rate of reaction, because all of them, they increase the rate of reaction. So always have that and then be able to do that. There was a question that was asked on the previous question paper that said we were given 3 experiments, A, B, and C, and they were carried out to investigate some of the factors that affect the rate of decomposition of hydrogen peroxide, and then which is given there, but identical samples of hydrogen peroxide are used. Now let's look at the question itself. It's saying in which experiment, A or B, so we're comparing between A and B, is the reaction rate higher? Which one will have the highest reaction rate between A and B? Let's look at the condition. They are both at 25 degrees Celsius. But when you look, A is without a catalyst, but B is with a catalyst. Definitely B will be your answer, will have the highest rate of reaction. And they are saying use collision theory to explain. So you are going to say, okay, a catalyst will provide an alternate pathway of lower activation energy. That is the first bullet. Then you're going to come back and say more effective collision per unit time. And you're going to say this is going to increase the rate of reaction. And then you are able to respond to that question. Now, chemical equilibrium. The most important thing here under chemical equilibrium is the definition itself to say what is chemical equilibrium. Define chemical equilibrium. Remember, we are defining according to the exam guideline. And according to the exam guideline, we are saying chemical equilibrium is the dynamic equilibrium. Is the dynamic equilibrium this one? Don't forget, we're saying it's a dynamic equilibrium. Before we say anything, we're saying it's a dynamic equilibrium when the rate of forward reaction, is equals to the rate of reverse reaction. So rate of forward is equals to the rate of reverse reaction. And then you are able to do that. Or you say the concentration of the reactants and the concentration of the products remain constant. Not that they are equal, but they remain constant. The other thing that is most important is that chemical equilibrium now is being affected by 3 conditions, which is your concentration, pressure, and temperature. No longer 6 like rates of reactions, but only 3 factors that are affecting our chemical equilibrium. So hence we indicated there. And don't forget that we have now endothermic and exothermic reaction, which is what we have done in grade 11. And then it's important to have this knowledge of your energy change to say forward reaction for this reaction is exothermic, because you can see we have more energy of the reactants than energy of the product. So when you compare the energy of the reactants and the energy of the product, you see that this is an exothermic reaction. And in this section now, because we have the reaction is reversible. So the reaction is reversible means that now the products can form the reactants. The product can be able to form the reactants, and then we are saying that now forward reaction is exothermic, which means reverse reaction will be endothermic. And if forward reaction is endothermic, like this one, forward reaction is endothermic, reverse reaction will be exothermic. Remember, we said exothermic reaction releases energy and endothermic reaction absorbs energy. And in this section, we are saying when you increase temperature, increasing temperature favors endothermic reaction. So you have that, and you know that decreasing temperature will favor exothermic reaction. So you will always have that with you to remember as we move. And this is the graph just to indicate your equilibrium, to say the rate of forward reaction is equal to the rate of reverse reaction. That is now the graph of the rate. It will say the rate of forward reaction is equal to the rate of reverse reaction. When it comes to the graph of concentration, we're saying the concentration of the reactant and the concentration of the product remains constant. So there are two graphs, the graph of reaction rate and the graph of concentration. And you see the difference now. In terms of the definition, we said the rate of dynamic equilibrium in which the rate of forward reaction is equal to the rate of reverse. You can see that they become one, which means that their rate are equal. But when it comes to concentration, they are not equal, but we are saying that the concentration of the reactant and the concentration of the product remain constant. Now, wanted to look at a question that is asking you what does the double arrow mean, and then definitely it will mean that the reaction is reversible, which means the products can be able to form the reactants. And then when you look at the KC problem given in a graph form, remember what I talked about, the issue of the bridge, to say we are given mass here, we're given mass there, and then you are able to see that, okay, when we are given mass, we must be able to convert mass to number of moles. So when you see mass, you know we have a mass initially when we are studying our reactant, the mass was 10,7, and at equilibrium, the mass is 8,1. Already, that's what we are going to work on using the rise table. Now, with no waste of time, we saw that this was a 1:1:1. So definitely you will take the mass that were given initially, which was 10,7, and then you will divide it by the molar mass. So always when you see mass, you think about molar mass. Small m, you think about big M, because you know that number of moles is mass over molar mass. And then you are able now to say 10,7 divided by 53,5, which means the initial number of moles is 0,2 for the reactant, but the products were not there initially, hence we have 0 and 0. And then if you check, the change always is in accordance to the ratio. So now if you check, we were given the mass at equilibrium of ammonium chloride at equilibrium there, to say, okay, we have 8,1 divided by 53,5, which means the mass at equilibrium is 0,15. Now we can be able to find the change. Remember the change. Now we are going to say, okay, if we subtract 0,15 from 0,2, we'll get 0,05. And then that is your change. And once you have one change, you are able to get other changes. How do you do that? You do like this, to say, I have 0,05 here. If this 0,05 is to 1 moles. So when I go up, I will divide. So it's 0,05 divided by 1, which is the number of moles here. When you go horizontal, you will multiply. To say, okay, 0,05 is still 1 mole here. I'll say 0,05 times 1, it will give me 0,05. The same, 0,05 divided by 1, it will give me 0,05 times 1 mole, it will give me that. So this ratio is always ratio in accordance with the ratio of the balanced equation. So it's very much important to say when you want to move from ammonium chloride to ammonia, you will go up to say 0,05 divided by the ratio, which is 1. You multiply by the ratio of the one you want in order for you to get 0,05. When you get 0,05, you divide it by its ratio, which is 1, multiply by the ratio of the other one that you want, and then you are able. So when you go up, you divide by the ratio. When you go to the right, you multiply by the ratio of the one you want. then you are able to get. Hence, because they are 1:1:1, you see your change is 0.05, 0.05, 0.05, because your ratio is the same. So always the change is in accordance to the ratio, and there is 1 mark for doing that. Another mark as well, you will have a mark of saying in the product side, you are going to add 0 plus 0.05 is 0.05. You get that. In the product you add, in the rectangles you subtracted 0.2 minus 0.05, they give you 0.015. So that is another mark. So you have a mark for ratio, a mark for addition and subtraction, and a mark of dividing by the volume, because we are given the volume. When you divide by the volume, you are able now to get that mark of dividing by volume, which was half, which is 0.5, hence the answer is 0.1 there. Remember, we are saying that the concentration of the solid remain the same, so we don't include that. We will just take it as a 1. Hence, when we write Kc, it will be NH3, concentration of NH3 multiplied by concentration of HCl. And then that will give you 0.1 and 0.1, which gives you 0.01, which is now your Kc that we have calculated. Remember, when it comes to Kc, we're saying that now a Kc which is more than 1, it means high yield. A Kc of less than 1 means low yield, which means in this case we had lower yield of the product. And then if you look now on the graph, I just wanted to remind you about the graph, to say when you analyze the graph, we're having the graph of nitrogen reacting with hydrogen gas to form 2 ammonia gas. This is an exothermic reaction. What happens if you look at T1 there? You can see that there is a disturbance at T1. What happens? There is a sharp increase of N2. So only N2 is increasing there. So you can see that the concentration of N2 was increased, or you can say N2 was added. And you know that according to Le Chatelain's principle, remember Le Chatelain's principle is saying that now if the conditions of a system that is at equilibrium, a closed system at equilibrium, are disturbed, a reaction will take place that will cancel the effect of the disturbance. What does it say? The Chatelain's principle: if the conditions of a closed system at equilibrium are disturbed, if one of the conditions is disturbed, a new equilibrium will be re-established. How? By favoring the reaction that cancel the effect of the disturbance. Please, you can't go to the exam room without knowing Le Chatelain's principle. So please, I'm emphasizing there. So we are saying, as we add N2, the reactant, as we add N2, equilibrium would be disturbed, because concentration affect the equilibrium. So equilibrium will be disturbed and a new equilibrium will be established. How will that happen? By favoring the reaction that cancel the effect of the disturbance. Hence, you will see that when we increase N2, forward reaction is favored. Why? Because we want to establish a new equilibrium. So when we increase a reactant, forward reaction is favored. Any reactant. When we decrease the product is favored. So forward reaction is favored under 2 conditions: when we increase the reactant and when we decrease the product. Forward reaction will be favored in terms of the concentration. Now, in here we're saying concentration of N2 was increased, and what happens when you increase the concentration of N2? The other one, which is H2, it must decrease so that a new equilibrium is established. And you can see that when we increase N2, H2 starts to decrease, now gradually decreases, and then NH3 forward reaction is favored and a new equilibrium is established. But now when the graph, all of them increase here in the graph, you can see that that must be pressure. When we increase pressure, all the concentration increase. When we decrease pressure, all the concentration decrease. So you got to know that increase in pressure increases the concentration of all the reacting species, all the species in the reactant and the product. So everything increases. So you know that in the graph, when all of them are behaving the same, sharp increase, you know that pressure was increased. But when there is a sharp decrease in all the concentrations, you know that that means pressure is decreased. So here we're saying pressure was increased, hence there is a sharp increase in the curve. Now, immediately when that happens, you will check. It's okay. If we increase pressure, how many moles? Always we are looking for gases to say we have 1 plus 3 gases, which means it's 4 moles of a gas in the reactants and 2 moles of a gas in the product. So if we increase pressure, it favors the least number of moles. Least number of moles is 2, which means forward direction will be favored. So you can see the forward direction is the dotted one, the ammonia one. This one is the forward direction is favored. Hence you see it gradually increasing. The other ones will decrease until a new equilibrium is established. Now at T3 then, you can see that there is no sharp increase of any concentration, not concentration of reactants or products. They are all not sharp increasing or decreasing. That shows you now that here we are dealing with the issue. We are dealing with temperature. Remember, temperature cannot, when you increase temperature, the concentration will remain the same. Hence, the graph now remains the same there. But because this is an exothermic reaction, if we increase temperature, remember what I said, increase in temperature favors endothermic reaction. So if you increase temperature, it will favor endothermic reaction. And if you decrease temperature, it will favor exothermic reaction. So it's important that we check now which one is exo, forward reaction. Is forward reaction favored? No. This dotted line here is decreasing, which means forward reaction is not favored. Which one is favored? Reverse reaction. You can see that the N2 graph is increasing and the H2 graph is increasing, which means the reverse reaction is favored. And reverse reaction is favored by increasing temperature. Remember, if forward reaction is exo, reverse is endo. And increasing temperature favors endo. How do we know? We see that the endo, which are the reactants, are increasing here, which means that the reverse reaction is favored. So important that you have that. I hope it helps you as you come across this question. Now, the final part of our lesson, which is based on acids and bases, summarized nicely on this one to say, when it comes to acids, lot of definitions, learners. We are saying, please ensure that you go through all of them. They are all simple definitions. You must be able to define them. Remember, we are defining an acid and a base according to Arenas, an acid and a base according to Lori Bronsted. Remember, Arenas said an acid produces hydrogen ion in aqueous solution, and a base produces hydroxide ion in aqueous solution. So you have that. And Lori Bronsted, they are saying an acid is a proton donor and a base is a proton acceptor. And we are saying now, once you know the definition according to Arenas, you know the definition according to Lori Bronsted, you must be able now to differentiate between strong acid and weak acid. Remember, a strong acid, we're saying it ionizes completely in water or in aqueous solution to form a high concentration of hydronium ion. So strong acid, we're saying it ionizes completely to form a high concentration of hydrogen ion, but it ionizes completely in aqueous solution or in water. It ionizes completely in water to form high concentration of hydronium ion, whereas a strong base dissociates. So with the base, we are saying it dissociates to form a completely, strong base dissociates completely in water to form a high concentration of hydroxide ion. So the difference between an acid and a base is that with the acid, strong acid, we are saying it ionizes completely to form high concentration of hydronium ion, whereas a strong base, we are saying it dissociates completely to form in water to form high concentration of hydroxide ion. Weak acid, it ionizes in completely in water to form low concentration of hydronium ion. And a weak base, we are saying it dissociates in completely. So as long as you are weak, it is incompletely. How is that important? Look at a strong base, for example. A strong base, because it dissociates completely, it will have a high Ka value, which means its Ka value will be greater than 1. So it's important when you're given a Ka value because it's showing you the strength of an acid. So when you see a Ka value of greater than 1, you know that this is for strong acid. And when you see a Ka value of less than 1, you know that that is for weak acid. So weak acid, because they ionize incompletely, in water to form a low concentration of hydronium ion, their Ka value is less than 1. The same with strong base. The Kb value for strong base will be greater than 1, and the Kb value for weak bases will be less than 1. So always know them by their Ka values. You are able to determine whether they are strong or weak. Another thing that I want to emphasize is the issue of concentrated versus dilute acids and base. Remember, when we say an acid is concentrated, just look at the formula itself of concentration, which is C equals to N over V. Concentrated means we have a large number of moles of the acid per unit in proportion to the volume of water. So we have less water added. So we have a large number of moles of acid in proportion to the volume of water. That is concentrated acid. Remember it with that equation. And when you are referring to dilute now, you will be saying it has less number of moles in proportion to the volume of water. So it means we have more water added, hence we are saying it's dilute. So you get such question, and learners sometimes make a mistake that if you have a strong acid that has more water added to it, they think that the strong acid becomes a weak acid. Remember, a strong acid is always a strong acid no matter how much water you add on it. But what happens is that a strong acid can be diluted by adding a lot of water. So dilute means we have less number of moles in proportion to the volume of water. I hope you got the difference between concentrated and dilute. The other thing now which is important is the issue of conjugate acid-base pairs. To say, how do I know the difference between an acid and its conjugate? For example, when you are having HCl, when you put it in water, reacting with water, forming H3O plus and then Cl minus. So you must be able to check that a conjugate is a lookalike. So HCl, definitely its conjugate must be Cl minus. Water, its conjugate must be H3O plus. What is the difference? You look, the difference is a hydrogen ion. The one with more hydrogen ions will be an acid. The one with the less hydrogen ion will be a conjugate base. So on the left of the reaction, we have acid and base. On the right, we have conjugate acid and conjugate base, which means in this case, HCl is our acid and water is our base. And H3O plus or hydronium ion is always a conjugate acid. As long as you have a reaction that forms hydronium ion, you must know it's a conjugate acid, and chlorine minus will be our conjugate base. So please always go to the exam with that knowledge of conjugate acid and base. And then the issue now of neutralization, as well as the issue of hydrolysis, which is the things that I would like to look at, and pH as I conclude. So already I've indicated the formula. We're still using the same formula, still following the same, but now the most important one is the Kavanaugh formula, that one, CAVA, for neutralization, for our titration. We're going to use that equation. It will help us. For pH calculation, we're saying pH equals to minus log H3O plus. Please copy the formula as it appears. You can see it's a small p, capital H there, so that you write it correctly. The ionization constant of water, this one, you are going to use this one, ionization constant of water, when you are given the concentration of a base and you have to calculate pH. Remember, we're saying the formula for pH is pH equals to minus log H3O plus. So if we check, if you are given OH, you must first come to this formula and substitute the OH there so that you determine the concentration of hydronium ion, and you are able to substitute there and calculate your pH. So it's very important to know that the ionization constant of water, when I'm given the concentration of a base, I have to calculate pH. I must use this formula so that I'm able to determine the concentration of H3O plus and put it in the formula and do my calculation. We talked about this: weak acid, Ka value less than 0, strong acid, Ka value greater than 1. And then we talked about the Kb value is less than 1 for weak bases, and Kb value is greater than 1 for strong acids. And titration, in terms of the process itself, in your exam guideline, it's written that you must know the steps to perform titration. Simplified in this one, where you can see all the steps that you are following during your titration. So you must know all the steps for titration. I've already talked about pH. To say our pH, we only do the pH calculation for strong acids and strong bases. Remember we said these ones, they ionize and dissociate completely, respectively. So when it comes to the weak acid and the weak bases, they don't ionize completely. So you don't know how much has ionized. Hence, now we don't know the hydronium concentration of hydronium ion. We're not certain about. But it becomes easier when you're dealing with strong acids and strong bases, because we are saying they ionize completely. Hence, we can use the mole ratio between the concentration of the acid and the concentration of the hydronium ion. We talked about that. And now I wanted to demonstrate here the issue of the limiting reagent. The issue of the limiting reagent, to say, let's say, for example, you are given a reaction between sulfuric acid and potassium hydroxide to form potassium sulfate and water. And this reaction tells you that for every 1 mole of sulfuric acid, it must react with 2 moles of potassium hydroxide. What is important here is that we must be able to use the mole ratio to compare the reactants. So it's 1:2. That is the mole ratio between the two of them. If we are given that the number of moles of sulfuric acid, for example, is 0.01, if this one is 0.01, and the number of moles of potassium hydroxide is 0.024, from the equation, we can be able to see that the mole ratio is 1:2, which means that 0.01 that were given for sulfuric acid, this is for the acid and this is for the base. For the sulfuric acid, we were given 0.01, which means 0.01 multiplied by 2 is 0.02, which means 0.01 of sulfuric acid can react with 0.02 of the base. Now that shows you that we had the base as 0.024, which means we have more base, but the acid is limited. Hence, we can be able to check that to say, okay, we have 0.024 of the base, which is more than enough, because we only require for 0.01 of acid, we require 0.02. How do we know? Using the mole ratio. So you are able to see that sulfuric acid is the limiting reagent because it will run out first. So we can say potassium hydroxide is in excess. It's important that you have that knowledge when you do calculations that are based on this one, which is the very last activity for this lesson, and then we call it. And then this was the question 2024, May, June. A standard solution is prepared by dissolving 10 grams of sodium carbonate. Remember, when you see grams, you see number of moles. Already you are saying, I must know the number of moles, then I must know the molar mass, because to get number of moles, when you're given mass, you must get the molar mass of this one, and then you know that number of moles is equals to mass over molar mass. So immediately when you know the mass is 10 grams, you must know the molar mass of sodium carbonate, and then you are able now to do your calculations with no problem. Look at the first question there. Calculate the concentration of the solution. So we always encouraging you of following this method. So we'll say, okay, number of moles is mass over molar mass. Then you are able now to say, I can take the mass is 10 gram, and then the molar mass of sodium carbonate, I think that is your 23 times 2, 46, and then plus 12 for carbon, plus 48. And then you are able to do the addition there. 48 plus 12, that will give you us 50, 60, 60 plus 26, about 86, yes, around 86. And then you are able to divide by that, and then you are able to get your number of moles. When you get your number of moles here, you must be able to say the question is concentration. So you must say C equals to N over V, which is your number of moles. You substitute there. But others will say, can't I just use the formula C equals to M over MV? It's allowed. Remember, you know the mass, you calculated the molar mass, you multiply by the volume. Volume is given as 0.7. So you're able to calculate the concentration. It will still be 3 marks. It's just that we want you to follow these steps so that you have understanding. But when you have understanding, you can just go straight to that formula and you'll be able to do your calculation, and with no problem you will get that. And then my molar mass, it was your 48 plus 12 plus that, and then the molar mass was 106. So look, it's the importance of using a calculator. And then you are able to say now is 10 divided by the molar mass of sodium carbonate, and then you are able now to see that, okay, you are having the molar mass of that, which is 106. You are having 10 divided by 106 times 0.7, and then you get your concentration, which is 0.13. Or you will follow that steps, 10 divided by 106, and then you are able to get the number of moles, which is 0.09. Then you go and use C equals N over V, 0.09 divided by the given volume, you get that. But the number of marks will remain 3, whichever the formula that you have chosen to use. Will the pH of the solution be greater than or less than 7? This question is the question of hydrolysis. Remember, hydrolysis, we are saying, is the reaction of salt with water. Hydrolysis, we are saying, is the reaction of salt with water. So what is our salt? Sodium carbonate. So you're taking sodium carbonate, you react it with water. You can first follow the steps to say you take a salt, sodium carbonate, and then you get the ions there to say, okay, we'll have 2 sodium plus, and then we'll have CO3 2 minus. Those are 2 sodium plus, and those are the ions. Then you can check where these ions come from. Remember, sodium plus is from sodium hydroxide. And then remember, carbonate is from hydrogen carbonate, H2CO3. So you can see that this salt is from a strong base and a weak acid. Remember, the hydrogen carbonate is a weak acid. So obviously, the salt here that will be formed there will be basic. It will be basic because the strong one always wins. So when you are reacting a strong base and a weak acid, definitely it will form like that. You can do that, or you can just take sodium carbonate, you react it with water, and then you are able to get your answer. So you are saying it will be greater than 7. Why will it be greater than 7? It will be greater than 7 because it's a strong base. Remember, strong base, the base is from pH of 7 to pH of 14. So because it's a strong base and a weak acid, then equivalence point would be on the alkaline or on the basic side of things. So you are expecting a basic solution, which means the equivalence point will be with the pH greater than 7. We'll have our equivalence point with a pH of greater than 7. Explain, which is what I was just did now, to say now your explanation is the reaction. You can take CO3, react it with water. You can take sodium carbonate, the whole of it, react it with water to form sodium hydrogen carbonate and sodium hydroxide. Or you can just take the ions, you react it with water. Remember, it will form HCO3 minus plus OH. And because this salt forms OH, hence we're saying it's a basic salt. Remember, a basic salt will form OH as one of the products. Now, the sodium carbonate solution is titrated with dilute hydrochloric acid. So you are having now that sodium hydrogen carbonate, which you said they are weak bases reacting with the strong acid called hydrochloric acid. The following indicators are used. I want you to have an understanding that this P is for acidic solution. That's when you are having a titration of a strong acid and a weak base. The solution would be acidic. And we are saying we use methyl orange there. We use methyl orange. The color change is from red to orange. So always have that to say the first range there is for acidic solution. That's strong acid and the weak base, which is what we are having here. So the indicator, if they ask you what is the indicator, it must be methyl orange. What is the color change? From red to orange. And then on the second one, where we are having a strong acid and a strong base, they are all strong. We know now we are going to have a neutral solution. Our solution will be neutral, and then the pH will be around 7. And we are saying now we use bromothymol blue. Remember, strong acid, strong base, we use bromothymol blue, and the color change is from yellow to blue. As we conclude, to say now, when you are having the pH around 8.3 and 10, there we're talking about now a weak acid and a strong base. Strong base, the solution will be basic. What is the indicator that we use? Phenolphthalein. And what will be the color change? Colorless to pink. So it's important that you know all that during your titration. You know which indicator I'm going to use, and then this information will definitely help you. And we are saying, if we are saying the solution is acidic, we are saying the equivalence point is at the pH of less than 7. The equivalence point there is around neutral. The equivalence point here is a pH of greater than 7, as we responded in the previous question. And then what is the question? Which one of the indicators will you use here? Already I've indicated that we have a strong acid and a weak base. Definitely we're going to use P as our indicator. And then why will you use P? Because we're titrating, it's a titration of a weak base with a strong acid. We said the strong one always win. And the solution will be acidic, as I've indicated, which I said we can use middle orange. The color will be red to orange. And the equivalence point is lower than pH of 7 because the solution is acidic. So it's important that you have that understanding as well using the equivalence point. And then we are having now the reaction there that I've given there, and then the reaction is potassium hydroxide and sulfuric acid to form K2SO4. The example that I was using for you when I was demonstrating the limiting reagent, to say we're given 0.01 of sulfuric acid, we're given 0.024 of potassium hydroxide, and we have seen that from here we're going to have 0.01 of this reacting with 0.02 of that, because the mole ratio is 1:2. So 0.01 times 2, we get that one. So you can see already that this is what we had initially, and this is what is going to react. What is going to react is that 0.02 of potassium hydroxide will react with 0.01 of sulfuric acid. And then you can see that when it comes to potassium hydroxide, there is potassium hydroxide that will remain. I think that will be potassium hydroxide in excess. We'll have potassium hydroxide in excess as well there. So it helps you as you deal with it. What is meant by a dilute acid? Already I told you dilute, that just go to the formula of concentration, N over V, say we have a less number of moles of the acid in proportion to the volume of water, and that is our definition of dilute. And then you are able to get your 2 marks there. Remember, it's 2 or nothing. So you must write the formula, you must write the definition correctly. We said it contains small amount or small number of moles of an acid in proportion to the volume of water. The same way I've been saying it to you. Now, as we conclude, the last question for the day is saying calculate the pH of the final solution. So this is where the science is, and it's important that you have understanding. Remember what we talked about. We talked about the reaction between sulfuric acid, H2SO4, and 2KOH to form the salt, potassium sulfate plus water. Now, if we check now, we had 0.01 of this, we had 0.024 of this one given. And we said because of the mole ratio, we're going to say 0.01, 1:2, 1:2. 0.01 will react with 0.02, because when you multiply 0.01 by 2, you'll get 0.02. So what is happening is that the whole, initially, you were given sulfuric acid 0.01, you were given potassium hydroxide 0.024. But now what reacted is that 0.01, all of it will react with 0.02, which means that now in potassium hydroxide, we're still having, if I say always number of moles initial is equals to number of moles that have reacted plus number of moles in excess. Always have that formula, it helps you. So you're able to see that what we had initially it was 0.024, but that which reacted is 0.02. So you can bring it this side to be minus 0.02. That gives you the number of moles in excess. So the pH is based on the number of moles in excess of potassium hydroxide, which now is your 0.004 there, which is a number of moles there. Remember, when you're having that, you must be able to convert that to number of moles to concentration. And then with no wasting of time, I will just explain it from here to say this is what you are having. You are having Number of moles of potassium hydroxide, we said is 0.02 that will react. And of that will react, we said the one that is in excess will be the 0.024, which is what we had initially, minus the reacted one, which is what I was explaining using that formula. And that gives you 0.04. And then now that you have this 0.04, which is the number of moles of potassium hydroxide, you can now calculate the concentration of the base. The concentration of the base is always C equals to N over V, which is now the number of moles, which is 0.04. You divide it by the volume. The volume was given as 0.2. So immediately when you divide that by 0.2, you're going to get your answer, which is 0.02 moles per cubic decimeter. And the pH, we want to calculate the pH. Remember, I told you that when you have the concentration of the base, you must go to Kw, which is concentration of H3O plus multiplied by concentration of OH minus, equals to 10 to the power of minus 14. Immediately when you substitute 0.02 there on the concentration of the base, you are able to get H3O plus concentration, and then you can write the pH formula from the data sheet. You substitute your 5 times 10 to the power of minus 13, you get 12.18. I hope you will practice this problem. It's your June 2024, and then I hope that will help you. I want to complete by saying thank you and good luck. I'm saying to you, when the question seems endless and your notes look like a foreign language, pause and remember, every reaction you write, every mechanism you solve is another piece of the puzzle falling into place. You are not just studying chemistry, you are training your mind to think critically, to solve problems, and to change the world. Keep going. The molecules may be small, but your purpose is massive. Thank you very much.